Hello everyone. Today we will be looking at a theorem which proves existence of nth root and uniqueness for any non-negative number. Let me start by writing the statement. So let alpha greater than 0 be a real number. We can consider greater than or equal to 0. Then for every natural number n, there exists x which is greater than or equal to 0 such that x raised to n is equal to alpha, and this x is unique. So if we take any non-negative real number, then we are claiming that we can find x such that x raised to n is alpha. So our x is like nth root of alpha, okay, and our further claim is that this x is unique. So how do we achieve this? So let us first discuss strategy of this proof. So this is not an actual proof, this is just the strategy. So if I draw the curve of the function f of x equal to x raised to n, it might look something like this, right? It will start from 0 here and it might look something like this. And if I draw a horizontal line at y equal to alpha, then both these curves will intersect here. So this is the point where I am supposed to have x raised to n equal to alpha. That's where they intersect. So how do I locate this point? So if I look on the left side of this curve, left side of this dotted line, then I know that for the points to the left of this dotted line, if I call them y, then y raised to n is less than alpha. So if I consider all the points for which y raised to n is less than or equal to alpha, and if I consider their LUB or supremum, I might get the desired point. That is the idea. Okay. Now, if I collect such points, then yes, I can find their LUB because this set is bounded. But I will have to then show that this LUB is the desired point. Now, what happens if that LUB is somewhere here? If that LUB is somewhere here, then we can always find a point in between this and this, the dotted line and the solid line, such that that point raised to n will be somewhere here, which is less than alpha, correct? So that point would be in our set, and that becomes an issue. On the other hand, if I claim that the LUB is somewhere here to the right of the dotted line, then I can always find another point in between these two, this dotted line and this solid line, such that that point raised to n is greater than alpha. So this also becomes an upper bound. So then this cannot be a least upper bound. Okay, this is the idea. So let us now formally write the proof. Okay. So by the way, we will consider alpha greater than 0 because alpha equal to 0 is obvious answer is 0. So case 1 alpha equal to 0, then take x equal to 0 and my job is done. X raised to n is alpha. So we have to worry about case 2 where alpha is strictly greater than 0. Now define S as collection of all those real numbers such that t is greater than 0 and t raised to n is less than or equal to alpha. Okay, t is non-negative and t raised to n is less than or equal to alpha. Now t is greater than or equal to 0. Okay, it doesn't have to be strictly greater. Now 0 belongs to S, therefore S is non-empty. Okay, because 0 raised to n will always be less than alpha since alpha is strictly greater than 0. So S is non-empty. Further, since AP1 states that set of natural numbers is not bounded above, there exists some n naught in n such that n naught is greater than alpha. Okay, I can always find a natural number n naught such that it is strictly greater than alpha. Now what happens to n naught raised to n? N naught raised to n will be greater than or equal to n naught for every n in n. Correct? If I put n equal to 1, they will be equal. But as soon as I put n equal to 2, n naught raised to n will be strictly greater than n naught, unless of course n naught is 1. And if n naught is 1, then also equality holds. So n naught raised to n is greater than or equal to n naught, and n naught I know is greater than alpha. Therefore, n naught raised to n does not belong to set S. Correct? And for every t in S, t raised to n is less than n naught raised to n, because we are already saying that the points in S have t raised to n less than or equal to alpha. So t raised to n is less than or equal to n naught raised to alpha. Hence, n naught becomes an upper bound for S. Correct? Because if I take any number larger than n naught, so if I take say r larger than n naught, then r raised to n will be larger than n naught raised to n, which is already less than alpha. So r cannot belong to S. So any number larger than n naught cannot belong to S. Hence, n naught becomes an upper bound for S. Therefore, S is a non-empty bounded above subset of R. Okay, S is a non-empty bounded above subset of R, and hence by LUB property S must have an LUB. By LUB property, there exists some C in R such that C is LUB of S, because I have a set which is non-empty and bounded above. Okay. And now my claim is this C is the desired nth root. That is, C raised to n is alpha. This is my claim. So we will consider two cases and rule them out as we discussed in the strategy. So what happens if C raised to n is less than alpha? Okay. So we said in the picture that this is the point of intersection. So this is alpha. So if C raised to n is less than alpha, means if C is somewhere here, okay, because C raised to n is then less than alpha, then between C and this point I can always find something else which has nth power less than alpha. Okay, so We'll try to work it out in a reverse way. Let me write the discussion here. So we want to find very small increment in C. Okay, we want to add something very small to C, and we want to make sure that that thing raised to n stays less than alpha. So we know that the sequence of reciprocals of natural numbers goes to 0. Okay, so I can find some k such that c plus 1 by k raised to n also stays less than alpha if c raised to n is less than alpha. Okay, so how do I do that? C plus 1 by k raised to n by binomial expansion. I can write this as c raised to n plus n choose 1 c raised to n minus 1 by k plus n choose 2 c raised to n minus 2 1 by k square plus 1 by k raised to n. This should be less than alpha. Okay. Now what I know about natural numbers is 1 by k raised to j will be less than or equal to 1 by k for every j in n. Correct? 1 by k is equal to 1 by k, but 1 by k square will be smaller than or equal to 1 by k because k square is larger than k. Similarly, 1 by k cube will be further smaller. Okay. So, if I consider just this LHS, then this LHS we know is less than or equal to c raised to n plus n choose 1 c raised to n minus 1 by k plus n choose 2 c raised to n minus 2 1 by k plus 1 by k. So if I take 1 by k common, then I have sum over j going from 1 to n choose j c raised to n minus j, correct? And this quantity does not have k, so this is some big constant. Okay, I will call that constant as, let us say, d. So this is anyway some constant, so if I can make c raised to n plus d by k less than alpha, then our job is done. Okay, and can we do that? So we want c raised to n, we want d by k to be smaller than alpha minus c raised to n, that is, we want k to be larger than d upon alpha minus c raised to n. So we want to find a natural number larger than this constant. Again, AP1 helps me. AP1 tells me that I can always find a natural number as large as I want. Okay, so this is the strategy, and from here we will work. So the formal proof says consider d equal to summation j going from 1 to n choose j c raised to n minus j. Okay, consider this d. Now by AP1 there exists a natural number k such that k is larger than d upon alpha minus c raised to n. By the way, remember we are in this case where c raised to n is less than alpha. Hence alpha minus c raised to n is positive, and hence I don't have to worry about the inequality sign here. Okay, it stays the same. So by AP1 there exists a natural number k such that k is greater than d upon alpha minus c raised to n. Okay, so we will keep this k in mind, and now we will consider this. Now consider the binomial expansion c plus 1 by k raised to n. So this is c raised to n plus n choose 1 c raised to n minus 1 1 by k plus 1 by k raised to n, and we will write this is less than or equal to c raised to n plus 1 by k common summation j going from 1 to n choose j c raised to n minus j, and this we know is d, so d by k. And from our choice of k, we know k is greater than, since k is greater than d upon alpha minus c raised to n, d by k is smaller than alpha minus c raised to n, correct? So this quantity becomes smaller than c raised to n plus alpha minus c raised to n, which is equal to alpha, okay? Thus, what we have proved? We have proved that there exists k in n such that c plus 1 by k raised to n is less than alpha, strictly less than alpha. Therefore, c plus 1 by k belongs to set S, and therefore this contradicts the fact that c is the least upper bound, because this c is no longer an upper bound. C plus 1 by k is in S. So this contradicts the fact that c is LUB of S. Therefore, this case is impossible. That is, c raised to n cannot be less than alpha. Okay. Now we will see what happens if I assume c raised to n to be greater than alpha. Okay. So this is my curve. So here suppose I have alpha line. So if I take c here, if c raised to n is greater than alpha, then I should be able to find something in between. Okay, that I will call as c minus 1 by k. So we'll use similar strategy. C minus 1 by k raised to n will look like c raised to n plus sum over j going from 1 to n choose j, and minus 1 by k raised to j and c raised to n minus j. Again binomial expansion, nothing else. But now we have a minus sign here, so we need to be a bit careful. Now, when I consider minus 1 by k raised to j, so this will be less than 0 if j is odd, correct? So if j is odd, then this is less than 0, and I know 0 is less than 1 by k, correct? So if j is odd, then I can write this, minus 1 by k raised to j is smaller than 1 by k, okay? But what happens if j is even? If j is even, then minus 1 by k raised to j is basically 1 by k raised to j, okay? So this I know is less than or equal to 1 by k, okay? But now what I want is, I want c minus 1 by k raised to n to be greater than alpha, okay? I don't want it to be smaller than alpha anymore. So I need a reverse inequality here. So using this, I can write minus 1 into 1 by k raised to j is larger than or equal to minus 1 by k if I multiply both sides by minus sign, correct? When j is so this happens when j is even. Okay, so this I can write as minus 1 raised to j plus 1 because I am multiplying 1 by k raised to j is greater than or equal to minus 1 by k. Okay, and if j is odd, then also I can multiply both sides. Okay, so basically in both the cases I can write minus 1 raised to j 1 by k raised to j is greater than minus 1 by k, because if the left hand side is positive, greater than or equal to, of course, if the left hand side is positive, then it is obviously larger than this negative number. But if the left hand side is negative, then we can prove that this is larger than 1 by k, because mod of 1 by k raised to j is smaller than or equal to mod of 1 by k. Okay, so we will use this fact. So I'm still not in the actual proof, okay, of this part. So c minus 1 by k raised to j, raised to n, we will write as c raised to n plus sum over j going from 1 to n choose j, c raised to n minus j, and n minus 1 by k whole raised to j. So this I will write as greater than or equal to c raised to n, and minus 1 by k raised to j is larger than or equal to minus 1 by k. So I will bring that outside, minus 1 by k, and this constant we will call as now d. Okay, so if I can find k such that this is larger than alpha, then my job is done. So let us try that. So my d stays the same. Okay, d looks exactly the same even in this case. So again, by AP1 there exists some natural number k such that c raised to n minus d upon k is greater than alpha. What guarantees that? Because this basically says that d by k should be less than c raised to n minus alpha, that is k should be greater than d upon c raised to n minus alpha, and I can always find that because now my c raised to n is larger than alpha, so I can always find k. So we will start with this. By AP1 there exists k in n such that k is greater than d upon c raised to n minus alpha. Okay, now using the binomial expansion, c minus 1 by k raised to n is greater than or equal to from here I will get c raised to n minus d by k. C raised to n minus d by k, which we know is greater than alpha. Therefore, c minus 1 by k raised to n is greater than alpha, which means c minus 1 by k does not belong to S, and c minus 1 by k is also an upper bound for S. but C was supposed to be the least upper bound for S. Therefore, this is a contradiction. Hence, C raised to n cannot be greater than alpha. We have already proved that C raised to n cannot be less than alpha, and now we are saying C raised to n cannot be greater than alpha. Hence, by trichotomy, the only thing that remains is C raised to n must be equal to alpha. Okay. Hence, we have proved existence of nth root via Archimedean property and of course LUB property. Okay. Now my next claim is about uniqueness, that this C is unique. This C is actually the X one. This C is the X that we want. Okay. So if suppose there exists X and Y such that X is not equal to Y, but X raised to n is equal to Y raised to n, and both are positive. Okay. So suppose this is not unique. So there are two roots, X and Y. And we are saying both are positive because we are worried about positive roots only. Then I can use expansion of this. X raised to n minus Y raised to n is X minus Y into X raised to n minus 1 plus, you know this expansion, so this is homework to complete this. But we know that this consists of all positive terms only because X and Y are both positive. Correct. And this is 0 because X raised to n is equal to Y raised to n. So that forces that this must be 0. Otherwise, if this is non-zero, then we are claiming that product of two non-zero numbers is 0, which is impossible. Okay. Hence, our C is unique, that is our nth root is unique. So we have proved existence as well as uniqueness of nth root. Let me stop here.